We're going to continue with our discussion of complex numbers, looking at a theorem I have up here on the board called, the pronunciation of this is up for debate, de Moivre's theorem. I'll call it de Moivre's theorem. Some people call it de Moivre's theorem or other variations. In fact, I just looked it up on Google, asked for the pronunciation of this thing, and the first three links I clicked on all pronounced it differently. So I can't tell you exactly. I'm just going to go with de Moivre's theorem, or de Moivre, or de Moivre. I don't know. De Moivre is good enough. So that's the way I'm going to pronounce it. But anyway, he's a French guy. Old mathematician, came up with this theorem. Basically, the theorem talks about powers and roots of complex numbers. Okay, so remember, we have the rectangular form of a complex number, we have the trig form of a complex number, and we have this kind of shorthand way of writing the trig form of a complex number. And here's just a first quadrant idea sketch of the if a complex number is a plus bi, it's a in the real side, b in the imaginary side, r is the distance to the origin or to zero, and then theta is the angle up off the real axis. Okay, so based upon that, we get these formulas we've talked about before. Now, if you were to take a complex number and raise it to a power, that can get kind of complicated because, depending upon how big that power is, if you're just squaring something, if you're just squaring like 2 plus 3i, that's not that big of a deal. You just do 2 plus 3i times 2 plus 3i and go through and distribute and you're good. But let's say you wanted to do 2 plus 3i raised to the 10th power. Well, now I've got to write 10 of those factors, right? And then distribute all of that. It's a mess. Well, there's some shortcuts, and it's the trig form that gives us the shortcuts. So, raising a complex number to a power is equivalent to raising the trig form to a power. If you raise this whole thing to a power, it splits between the two factors. So you're raising r to the power, and you're raising the cosine of theta plus I sine of theta to that power. Oh, it's not 2, it's n. Okay? Now, if you were to expand this out, now this expansion is just as messy as doing the a plus bi expansion. However, we have some trig identities that we learned before, the sum identities for cosine and sine, that help us out with this. When we expand this out, if you apply these identities over and over again, you'll get some generalizations. I'm not going to go through all the arithmetic because it would fill up my small board here. However, the formula comes from a repeated application of these formulas. And so the result of that is r to the n times the cosine of n theta plus I times the sine of n theta. What's interesting, and what you might notice when you get into this a little bit more, is if you have a and b, the two angles are the same, if they're theta and theta, then you start getting, if I were to expand this out, powers of sines and cosines would be like cos A or cos theta, right? That's cos squared theta. And that's where the double angle formulas come from as well. But if you expand that out to third powers and fourth powers and so forth, then you end up really combining the terms. So you're adding the terms together. Well, if it's theta and theta added together, then you get 2 theta. Or if it's n thetas added together, then it's n times theta. That's where this comes from, okay? So just without going through the details, that's where this comes from. So essentially, if you want to raise the power on a complex number, say 2 plus 3i raised to the 10th power, you first find the absolute value, then you find theta, you raise the absolute value to the 10th power, whatever the power is, you multiply theta by 10, and then just put it in this form, and you get the power. okay? So it's actually a very simple calculation, way simpler than putting 10 factors of 2 plus 3i and trying to multiply all that out. I'll give you an example. In fact, let's go ahead and work through that. 2 plus 3i raised to the 10th power. Well, all we have to do is find r and theta. Well, the r value for 2 plus 3i is the square root of the sum of the squares, 4 plus 9. 4 plus 9 is 13, so it's the square root of 13. Okay? So r to the n would be the square root of 13 raised to the 10th power. And then you multiply. Now we got to find the angle. The angle is found using the inverse tangent of it's 3 over 2, right? It's the b over a. And that one I'm going to need my calculator for because it's not one of our nice triangles. Inverse tan 3 over 2. Now this is going to be an approximate value, obviously. It's about 56.3 degrees. This is a first quadrant angle and it is consistent because this point is in the first quadrant, so we don't need to make a quadrant adjustment there. And so then I want to calculate the cosine of 10 times the angle, right? Because I'm raising it to the 10 power, so it's 10 for n. The angle is that, so it'd be 563 degrees, right? That's 10 times 56.3. Plus I times the sine of 563 degrees, okay? And so then I calculate this, and I'll get the values for, 2 plus 3i raised to the 10th power. The square root of 13 to the 10th, well, power to a power, right? The square root is a power of a half. Power to a power, you multiply the power, so half times 10 is 5. So this is the same as 13 to the 5th power. Times that cosine and the sine. All right, and so then I just type that into the calculator and I'll get our values. So first of all, 13 to the 5th power is not a small number. It's 371,293. The cosine of 563 is negative 0.9205 roughly. And the sine of the same thing, 563, is, it's negative also, 0.3907 roughly, okay? And so if I multiply my magnitude here times those two things, so 37,1293 times the cosine of 563, I'm going to get negative 341,777 with some decimals. I'm rounding it off. Minus, I'll do the same thing, but I'll put the sign in there. Looks like 145,076 roughly times I. Okay, again, I'm rounding to the nearest whole number on those. All right, and so these are the values you would get if you were to take 2 plus 3i, raise it to the 10th power. That's 2 plus 3i times 2 plus 3i times 2 plus 3i 10 times. Distribute all that out 2 at a time, and then add it all together. Of course, every time you hit an I squared, you make it a -1, and there's all those details that you have to work through very carefully. Rather than doing that, this is way simpler, right? So you raise the magnitude to the 10th power, multiply the angle by 10, you'll get exactly the same thing. And you can do this on your calculator just to check. If I take the quantity 2 plus 3i, and remember your calculator has the I button on it. If you have my same calculator as me, it's the second feature of the decimal. You go 2 plus 3i, raise that to the 10th power, and what I get on the calculator, well, it's off a little bit, but that's because I rounded some things. My calculator is telling me that this is approximately, maybe I'll change my color here. Well, it's telling me it's equal to negative 341525. That's actually off by a little more than I thought it would be. Minus 145668i. Alright, so the calculator is giving me this value, whereas I'm calculating this value. Again, I rounded these angles off, and I think that's where the error is going to come from, is in rounding those angles. I did not round here on the 13 to the 5th power. That one I kept the same, or the square root of 13 to the 10th, same thing. I didn't have to round there. So the error is coming in the rounding of that angle, right? I used 56.3, but it's not. It's 56.3 and then some other decimal. So that's where that error is going to come from. But you can see that the values are very close. Technically, I probably should have rounded those off different spots to get the right significant digits, but it's close enough for what I'm trying to convey to you right now. Okay, so I'm just checking the answer. Okay, so that gives you an idea of how much easier de Moivre's theorem is compared to just the mechanical multiplication of this thing 10 times. Of course, most of these you're not going to be doing that large of powers, but you could, and so that's why this works out well. Okay, so we could do more examples of this. And some of these will work out a little bit nicer. So something like, I don't know, maybe 1 minus I root 3, and raise that to the 4th power, for instance. 1 minus I root 3. Well, 1 minus I root 3, that means the A value is 1, the B value is negative root 3. That's going to be in the 4th quadrant, right? 1, negative root 3. So that's a 4th quadrant angle. If I then try to find R and theta, R is the square root of the sum of the squares. That'd be 1 plus 3, right? This one squared is 1, this one squared is 3. That's going to be the square root of 4, which is equal to 2. Nice. Okay, that one worked out well. And then theta is going to be the inverse tangent of b over a. So that'd be negative root 3 over 1. Well, the inverse tangent of root 3 is actually one of our nice angles. Inverse tan negative, well, yeah, it's root 3. I was going to do the negative on there, but yeah, it should be 60 degrees. Now, 60 degrees with a positive, but it's 60 degrees in the 4th quadrant, so that's going to be 300-degree angle. And if you were to actually put that in with a negative, that should work out. I'm just double checking. Well, it says negative 60 on my calculator. Of course, the inverse tangent is only going to give you angles between negative 90 and 90 if you're in degree mode. So remember, you just have to convert that. So it's a 300-degree angle. So if I want to find this value, it's going to be the R value raised to the n power, which in this case is 4, times the cosine of, well, 4 times 300 is 1200. So 1200-degree angle plus I sine of 1200. Okay. So then we just calculate that, right? We just plug that in. Of course, 2 to the 4th power is 16. And then I think those angles might actually work out nicely. I'm not sure. Let's see, we get 16 cosine of 1200. and that is negative 8. Cool. So I think the cosine of 1200 then must be negative 1/2. So that equals negative 8. And then here the sine of 1200. Now that's a decimal. But think about this. If our cosine, if that's negative 1/2, this has got to be on a 30, 60, 90 triangle somewhere. So think about what 1200 is. 1200 degrees, if you think about that and put that between 0 and 360, if you were to divide 1200 by 360, 1200 divide by 360 and try to figure out what the remainder is, that equals 3 1/3, right? So 3 times around and 1/3 of the time around. Well, what's 1/3 of 360? It's 240, so this would be a 240 degree angle, right? 240 degree angle is a 60 degree angle down in the 3rd quadrant. So this is equivalent to the cosine of 240 and the sine of 240, right? Cosine of 240 is your negative 1/2. Double checking. Yep, negative 1/2. And so the sine of 240, if you think about that, with a 30, 60, 90 triangle, 1, 2, root 3, the sine, if the cosine of the 60 is adjacent over hypotenuse, sine is opposite over hypotenuse, root 3 over 2. So that's going to be 16 times root 3 over 2 I. 16 over 2 is 8. Okay. And it's a negative because it's in the 3rd quadrant, right? The sign is negative, so that should actually be a minus. There it is. Okay. So hopefully that's making sense. I've got the 16 times the negative 1/2 is my negative 8. 16 times this sign, which is negative root 3 over 2, gives me this expression. Then I just have to simplify that. So 16 over 2 is 8, so this becomes negative 8 minus 8 root 3 times I, or 8I root 3 is probably how you would want to write that, because we put the roots at the end. Okay? Cool. Now, what is 8 root 3 as a decimal? 8 root 3. It's about 13.856. So I'm going to double check this, make sure it works. If I do the quantity 1 minus I root 3, raise that to the 4th, and I get that. Yes, it works out. So if you can see here, my 8 root 3 is this 13.8 or whatever it is there. So when I take this to the power of 4, I get my negative 8, which I calculated earlier, and then I get plus 13.8 times I. Okay, so it did work out. It actually worked out very well. So this 8 root 3, that's what I had to calculate, because your calculator won't give you the root in exact form. It won't tell you square root of 3. So you just have to deal with the decimal to get that check. Okay, but this is a nice way to get an exact form or exact value of that power.